Well, hello everyone, and thank you for joining us for today's webinar on the implementation of solar photovoltaics in municipal facilities. My name is Catherine Wilson. I'm the program manager of the Mayor's Megawatt Challenge, a program working with municipalities since 2003 to reduce energy use and greenhouse gas emissions in their own facilities. I'd like to take this opportunity to thank our program sponsor, Enbridge Gas, who have been helping us and our municipalities achieve our objectives. So for the past few years, particularly following the 2019 climate emergency declarations and the establishment of net zero targets, members of the Mayor's Megawatt Challenge have been hard at work developing low carbon plans for their buildings. Now, with the plans in hand, the focus is now shifting to the implementation of the plans. So not just what is going to be done, but how it's going to be done. So Enerlife Consulting provides the technical direction for the program and have completed close to 100 low carbon plans for a range of municipal building types. The findings show that solar PV is often a cornerstone of the plans and has the potential to offer significant greenhouse gas reductions, positive financial returns, and long-term electrical savings. So recognizing these opportunities, our member municipalities expressed an interest to explore the topic further. So just some housekeeping items before we get started. If you have any questions related to the technology or non-content related questions, please enter them into the chat. If you have questions related to the content itself, please use the Q&A option. Depending on the nature of the question, some questions will be addressed live in the Q&A and others in a Q&A session following the presentations. And here's the agenda for today. So Cajun Singham, he's the Enerlife technical lead for the low carbon plans. He'll set the stage by providing some background information on the technology, the various options available, the pros and cons of the different options. He'll also share some of the high-level results from the studies that we've done and things that should be considered when moving to the implementation stage. We'll then explore the City of Toronto experience and then hear about some of the incentives out there to help fund the projects. We'll then have a panel discussion following the presentations, and the audience will have a chance to ask questions. So for the panel, before jumping in, I'd like to extend a warm welcome to our presenters who will also take part in the panel discussion. We have Rick Wu from the City of Toronto, who will share his experience with solar PV projects. Things to be mindful of during the implementation of the projects. We will then hear from Mohammed Youssef from the IESO, who will share some information on their current incentives that are being offered and how you can take advantage of those. We have Amandeep Dewal, Director of Engineering at Enerlife, who will moderate the discussion following the presentations. Unfortunately, due to some unforeseen circumstances, Sajeev from the City of Sudbury is not able to join us today, but we hope to share his story at some point in the future. So let's jump right in, starting with some background information to set the stage and some key terms that will be mentioned throughout the webinar that's useful to understand those. So what is solar PV? Well, these systems convert sunlight into electrical energy that can offset the electrical consumption for your building. Behind the meter generation refers to technologies that generate energy on the customer's end of the utility meter, and solar PV is included in that. Load displacement, you'll hear that quite often throughout the session today. Load displacement occurs when the electricity generated from the solar PV system is exclusively used to meet the electricity consumption needs of the building. Whereas net metering allows customers to generate their own electricity using solar panels and receive credits on their electricity bill for any excess power. Set back to the grid. And I will now turn it over to Cajun just to quickly introduce himself and to dive into the technology. Cajun.
Thanks, Catherine. Hi, everyone. Cajun here. So I'm just going to go into a bit of high-level concepts on PV. And, first step would be understanding what the technology is. So PV has matured in the last 2 decades, more than 2 decades. And when people think about PV panels, or when I say PV, it means photovoltaic is the full term. And when you imagine a PV panel, you're probably thinking of poly and monocrystalline panels, which is the most ubiquitous, used in all kinds of building types and arrays, whether it's on ground mount, roof mount, or even the carports. And that's what you're really seeing when you see a lot of implementation on PV. There's new technologies like bifacial panels, which can use um, the light reflected from the ground. So it's able to capture solar energy from the top and the bottom surfaces. It just improves the efficiencies. You have about maybe 5–10% efficiencies of improved efficiencies over a typical solar PV panel. These are best used in things like carports. There's also newer systems or newer PV designs like thin film that's coming out. They have, pros and cons. Thin film is lighter weight, doesn't have as much mounting requirements or restrictions as maybe the poly monocrystalline or bifacials. And they'd have a much lower efficiency and lower life expectancy. But that's a balance that you get for that weight and cost. And they do come a bit more affordable. Different mounting systems exist. They have also improved. I know in the past, a lot of people were concerned about maximizing the angle so you can maximize your generation at a specific moment in time. Uh, of course, that had its own drawbacks, things like snow loads, wind loads. Um, Modern designs, when you're looking to just maximize generation and not just a peak generation, like annual generation, um, you're able to go lower angles. This helps reduce the wind loads and snow loads that some of these buildings might have been facing, and a lot more different mounting systems, such as rail design or other weight distribution systems. So that's a quick note on some of the technology that's come out. There's a lot more technology that's available, like building integrated PV systems, PV thermal systems. Not a lot of that has gotten traction in Canada, but a lot more in Europe. Maybe we'll see that in the future. Catherine, next slide. To continue on for the technology that we have solar inverters. So these PV inverters, they're advancing quite a bit from what they were in the past. They're able to convert this energy a lot more efficiently. Efficiencies have improved. More importantly, they're able to monitor, verify, and track the information, and especially for net metering, a lot better. They are one of the most often replaced pieces of a PV system. They require replacements every 10 to 12 years. They are probably the unit that fails the most often compared to PVs, which are pretty durable and long lasting. With at least considering polycrystalline and monocrystalline PV panels. There's a lot of opportunities when using solar inverters and incorporating them. There's different types of solar inverters like microinverters, central inverters. There is a preference to central inverters that we find, uh, mainly because it's a lot easier to access, maintain, and likely less failures. The other technologies that are useful for PV design is battery storage for peak load shaving and using excess generation to be used at different times. The cost of battery storage has gone down quite a bit also. There's a lot of benefits, mainly on the electricity demand side of things. Like if you have a Class A facility for global adjustments, you're going to have a lot of demand costs, and battery storage can help reduce those loads at those global adjustment hours. They can be used as short-term buffers for a day or two, depending on how big of a battery bank you're going to be installing. You probably won't have a battery bank that can last a whole season, which is where the grid and net metering really comes in handy for buildings that have a lot of variable loads. Cost is the biggest factor when it comes to considering battery storage, mainly because of the amount of lithium ion or whatever battery technology that you're using, the space required, the weight, and that they do have a life expectancy. They don't last forever, they degrade over time, they require replacements. So that's a quick note on the technologies for PV, for the entire PV systems. Catherine, next slide. And now we're going to be going into a bit of different types of PV installations. So one of them would be the rooftop arrays. a lot of benefits, pros and cons to these kind of things. One of the benefits, some of the benefits of rooftop is that there's reduced risk of shading, minimize your footprint. You're already using available roof space. It's elevated, so you have uh, less risk of shading from trees or other structures around the space or the facility. There's a lot of already existing systems, a lot of experienced installers. It's been matured over the last few decades, more affordable than ever. Uh, you know, you might have seen those charts of PV dollar per watt exponentially decreasing. It might be hitting a flat line sooner or later, just like transistors. Technology does find a sweet spot and may stay at that level for a while until there's something even more innovative that comes along. Uh, when we look at the various technologies like crystalline silicone and thin film panels, they accommodate different needs, whether it's weight restrictions or curvatures or weird angles on the roof or whatever structure that you're placing these panels on. Obviously, mounting systems can also accommodate depending on your cost and how much capacity you're looking for. Uh, Generally, rooftop arrays have a long lifespans. We do acknowledge that there's, rain, snow, wind, all these things, but for the most part, they're easy to clean. At least the crystalline silicone, so the poly and monocrystalline PV panels. We rarely hear stories about the panels themselves failing unless they crack from whether something falling from the sky, hail, things like that. There are always risks for these kind of things, but they're for the most part, durability has improved significantly over the last few decades. Limitations are, the roof type. Flat roof obviously gives you the easiest installation. Pitch roof, a bit more challenging on the weight distribution, but you can still do that. Curved roof, a bit more challenging than the pitch roofs. You just have to make sure that your your weight distribution is matching with the existing structure. Um, Looking at how to access could be a challenge on the roof, so you should be making sure there's enough uh, ac access pathways, access locations, that people can go on the roof and do the maintenance or checks and balances as they need. Low capacity systems are typically a lot more expensive. PV is one of those things that scale well the higher capacities you go. Structural loads, uh, they need to be evaluated. That's one of the biggest uh, components for looking at PV, especially on the roof, is can the building sustain this weight? Is this structure, the roof structure, whether it's trusses or whatnot, was it designed to have more weight? Can you remove gravel or other components on the roof to be able to provide more capacity to these, to be able to install PV? These are considerations that you have to take, talking with a structural engineer. And because of that, monocrystalline and polycrystalline panels are higher weights. Um, they have better efficiencies, last longer, but there are thin film panels, lower lifespans and lower efficiencies, but cost less. But thin film panels are not as ubiquitous, so you'll likely not find that many experienced installers. Next slide. The other system types that we'll find are PV carports. When PV or photovoltaics on the roof is not as feasible, whether or not it's because you just don't have the roof space or you have a bunch of RTUs or other systems taking up space, that might be causing shading issues. You can look at PV if you have a large car parking lot. So you can use existing spaces. Carports are great because they can offer shading, especially in the summertime, shelter for cars, charging ports for electric vehicles. They use bifacials, so they'll generate more than a typical panel. So per square meter of panel, you should be getting more generation. They're minimal in design because they're, a lot of them are already packaged with the pre-built structures, and you can mount the PV panels on those. Easier to maintain. You'll have easier access to inverters. You don't necessarily need to climb up a roof. You might need to have some things that can help you access cleaning off snow if you need, but most of these snow loads, because of the angle of the carports, will just slide off. Limitations is that it's quite a bit expensive. It's almost more than double the cost of what you would see for a similar area size for a rooftop system. They require large parking lots, like I mentioned. PV scales with how large the areas are. So economies of scale, the larger it is, the more affordable and more positive your NPVs, your net present values, if you're evaluating life cycle costs would be. There are fewer installations. So again, not as many people have done these installations, so you might not find as many experienced contractors. And there's limited choices available. You're not going to find all sorts of mounting structures available. There's a very, it's not the biggest market, is what I'd add. Next slide. And the last, but not least, there's a lot more, but for what we're going to be talking about today, ground mount is another one. Benefits are that it's great for microgrids, utility level installations. You can orient these ground mounts to maximize PV generation, going back to how maximizing the angle to get the most generation at different times. You can have complex angles and rotations and tilts if you really wanted to. That will add a lot of cost to the system though. It's a lot easier to maintain because it's lower levels. You're not climbing ladders or getting onto any roofs. They are not as complex. These systems have existed for many decades, I would say even 50 years. So there should be a lot of experience on how they're installed and operated. Limitations is unlike carports or PV roof arrays, which use an existing space that's just hasn't been tapped into, like parking lots or roof. A ground mount would take up a large footprint that likely won't be used for any other systems or components. And if you are planning on using tilts and axis trackers, that does add a lot of cost. And you might want to consider protections or shelters from unwanted interference, whether it's people in the neighborhood, wildlife, squirrels. I've heard stories about squirrels and things that have bit through some wires. So little things like that you'd want to consider making sure that these systems are protected from. And next slide. So we've done a lot of PV studies, solar PV studies in the feasibilities projects that we worked on decarbonization, or we've investigated a lot of municipal buildings, whether it's been town halls, community centers, libraries, public works garages. And there's a lot of options and opportunities for PV. PV in general has been a good measure to help bring down buildings to become more low carbon. Obviously, this is going to be a different impact in different provinces. In Ontario, we have a pretty clean grid. You might see something differently in Saskatchewan or in Alberta. Manitoba also has a very clean grid. So you're not going to be getting as many emission savings, but you can still get a lot of cost savings. And there's a lot of funding available when you do deep retrofits, maybe not specifically for just PV. In Ontario, we will have Mohammed speak of some new incentives that are coming out. And generally, there is a high positive net present value. It does depend on the existing operations, how big of an array you're using, the net metering that you have available. I would say buildings like arenas definitely require net metering because most of your consumption is going to be there, or at least seasonal arenas will be in the wintertime where you're not going to get the most generation versus in the summertime. So connecting with the grid for those specific building types really helps. Buildings like offices, town halls, it's not as critical because it's a fairly consistent load throughout the year. And on our projects, we've seen about 64% of the projects without funding had a positive NPV. 87% of the projects with 20% funding or CBR funding from the FCM was seen to have a net present value, a positive net present value. And 51% of our projects had a net present value of more than 100K. So it's not just on the fence. And our largest areas that we studied were from 838 kilowatts, so pretty sizable array, and the smallest is 30 kilowatts. We wouldn't really recommend going too small because, like I mentioned, the economies of scale really limits the ability to get the most out of the arrays for the cost and the replacements of the inverters that go on. And that is a quick summary of our projects and some context on PV. And I'll just continue on this for solar PV implementation considerations. As we've gone through a lot of our projects, we've considered what you need to understand about your specific landscape in your specific locations. So local regulations and incentives, you'll have to approach your local distribution companies, your utility companies, LDC for short, for specific limitations, constraints. Do they have feeders? Do they have capacity at the lines? Can they do net metering? Is there a bidirectional capability at those locations? You'll have to be able to look at their existing infrastructure and policies that they may have. You would require to work with your LDCs, whether it's to ensure that they have capacity, so they know that you are planning a project like this, submit connection impact assessments. You do require an electrical single line diagram. This will be something that you'll likely be doing or you'll have available after you've done a more detailed design. This SLD or single line diagram will be submitted as a part of the connection impact assessment, and that can take up to 6 months. Usually this design phase or this communication phase isn't the longest from what we've heard, but we'll continue on for the next part. There is also high-level solar design that I want to mention, which is just checking, before you really do any of the CIA or the connection impact assessment or create any electrical drawings, find out if your building is even in a good position. You might have a available roof space, but you have trees that are taller than your roof that would end up shading your building. You might have a roof space that's only facing the north that might not maximize how much generation you get for the investment you're going to be putting in. So some things will rule out projects. You might immediately find out that you only have like a thin sheet for a roof, and that's not going to really support any weight. So you can rule out projects immediately at the beginning before you really dive into doing CIAs or anything for the. An LDC is really just a utility provider. It could be Toronto Hydro or any other local distribution company, so people that are delivering the electricity. And do these need to be Class A to achieve positive net value or net present value? I'm getting my acronyms mixed up. All right, so do they need to be Class A? Not necessarily. I would say that net metering likely benefits more towards Class B customers because of how the credits work. They don't necessarily, most utility companies will not credit for the delivery or distribution, just the energy consumption. Usually that's the kilowatt hours. They don't all also discount the demand. So you will probably have a better net present value when you're a Class B customer. When you're a Class A customer, you'd want to be focusing on demand reductions. So you'd want to use more on site. So I guess I'm talking about net metering still. But a lot of projects a lot of the projects that we worked on are community centers or facilities that have a lot of variant loads. So we did focus on net metering quite a bit. But I think you will still have a good opportunity to get a positive net present value when you are a Class A customer because you can shift down your loads, like I mentioned. Shaving your peaks can make a big difference, especially since your peaks usually happen around daytime. Q&A questions, I will look at that at the end. So going into the next slide. All right, so more considerations for implementation, validate and check against your electrical and structural requirements. Make sure that you don't need any major upgrades. And when you do this, like the portions that you'll be doing is the structural investigation or assessments. electrical assessments, you'll need a structural engineer, an electrical engineer to help you. This is where you'd make your single line diagrams, find out if you need any upgrades or any infrastructure upgrades for your structural, find out if you need any reinforcements. If you do need reinforcements, that usually rules out the business case. But most often with the current mounting systems that are available and all the advancements that have been made, minimizing wind losses, snow loads, things like that, most often you are able to do a PV panel without any reinforcements, but you might hear from Rick, a lot does get ruled out regardless. And this might impact your insurances. So make sure you're able to review how that might impact your insurances, any other restrictions as you do these assessments. Next question, or next slide. So after you've done the investigations, you got your electrical assessments done, and you can confirm that the capacity is there. You don't need any structural reinforcements. You can do the detailed solar PV designs. Do your selections, create your single line diagrams for your array, finalize all this, submit it for the CIAs. On the implementation side, finding experienced contractors. If you have turnkey solutions for full package installations, that'd be great. Coordinate with all parties, like the LDCs, utilities, your own operations staff, make sure that they understand how these systems are operating and being used or need to be maintained. And maintenance and durability. One thing you'll hear quite a bit from our other speakers is that the panels don't necessarily require a lot of maintenance, and the inverters are really the key point to failure. And you'd want to be making sure that you have access and a design that encourages ease of replacements for inverters. That would be a high-level summary of these systems, and I think we can pass it on to the next speakers. Thank you.
Perfect. Thank you so much, Cajun. I apologize for any transcript that I can't get rid of. That was distracting everything. If anyone, well, I think there's quite a few questions in the Q&A. Cajun will try to get to those if he can address them during the session. Anything he can't, we will circulate in a Q&A document after the webinar. Okay, thanks again, Cajun. I would now like to turn it over to Rick Wu from the City of Toronto. Thank you so much for joining us, Rick. If you would like to quickly introduce yourself and then tell us your story, we're really looking forward to hearing it.
Just to make sure I got my mics on, you can hear me, right?
Yes, can hear you
Okay.
perfectly.
Good afternoon, everyone. My name is Rick Wu, Senior Engineer from City of Toronto, Environment, Climate and Forestry Divisions. Today, I'm excited to share our experience with implementing rooftop solar PV system on municipal buildings. This presentation will walk you through the process, challenges, and the insights that we have gained through our various projects across the city. Thank you to Mayor Megawatt's challenge, an opportunity to share our journey. Next slide. The city of Toronto has been integrating rooftop solar PV across facility as part of our border sustainability and climate action goals since 2009. From FIT program to now net metering projects, there are about 110 rooftop solar systems among the city facilities, total at about 10 megawatt power. This presentation outlines our step-by-step implementation process, highlights key technicals and operation details, and share some lessons that we have learned, and discuss some special cases such as installations on a curved or sloped roof. We'll finish with a Q&A sessions to cover any additional questions you may have. Next slide. Implementing a rooftop solar PV system isn't just about putting the panels on the roof. It involves a structured process. First, we will identify the buildings through a pre-screening process that looks at the roofing age or any re-roofing plan. Then we will perform a structural capacity assessment, followed by a preliminary solar PV system design. The output of the design will be used for our DER pre-approval with Toronto Hydro and establish a business case for the project. With all the feasibility assessment completed, we will move to a procurement of the project and the construction phase follow, ending with the testing, commissioning, and monitoring of the system. Each phase has a specific milestone and stakeholder engagement points to ensure a smooth delivery. Next slide. Let's dive into some of the technical and logistical details. During the feasibility study, we'll assess the site, future roof replacement or roofing age, the type of roofing, such as two-ply modified bitumen, BUR, inverted, single-ply, and so on, the roof structural type and material, as well as the type of building, such as emergency services. Then in the structural assessment, we will review the capacity of the roof for a typical ballast system and review other system option if a ballast system is not feasible. We will perform a preliminary system design using commercial solar PV software, such as PVSys or Helioscope, to estimate the expected output, the generation, and the financial payback for the system. Next slide. Continue from previous slide, then we will submit a DER pre-approval to Toronto Hydro to confirm the available capacity for DER connections. This is one of the most crucial steps to confirm the projects can be proceeded. Using the generation estimate from the design and the building electricity account type, we can prepare the financials of the project to determine the business case. Procurement strategy is critical. We use design build or EPC type of contract, as well as a general contractor and a subcontract, depending on the project complexity. We spend a lot of effort in the procurement to ensure proper design build and desired outcome is achieved for the projects. Next slide. So here is a sample business case that I have compiled for the latest net metering and load displacement project. One of the interesting thing is with the incentive included, it is noticed that the business case can significantly or the payback can significantly decrease with the help of the incentive. And also, if you notice that depending on the account type and the types of buildings, the paybacks also varies. And one thing is really interesting, as mentioned in previous sessions, the Class A and B, and also under 50 kilowatts, they all have different accounting for the demand charge as well as the hourly energy cost, and that will have an impact on how the payback or the business case is calculated. These estimate is based on a hourly simulations using Ontario hourly energy price as well as the hourly demand from the utilities. Okay, next slide. So here is a sample electrical drawings from a solar PV project. It is noticed that for net metering, we are behind the meter, and the connections is depending on the building electrical infrastructure. In this case, we can actually tie into a secondary panel located after the step-down transformer. This system on this is a community center that was located in the city of Toronto, and we maximize all the roof area in terms of the for the solar PV install, and this project also this community center is also a multi-use facility, including a outdoor swimming pool, as well as a childcare center attached to the building. So this single line diagram will be part of the CIA or the connection impact assessments required by your local energy electricity provider. Okay, next. So through our experience with the implementing rooftop solar PV projects, we have gathered a number of important lessons that we can benefit for future projects. Let's walk you through a few of them. Preliminary work is very important. One of the biggest takeaway is the value of a detailed preliminary study. This includes the site assessment, roof structure reviews, hydro capacity review, as well as coordination with stakeholders early in the process. Second, the design tender versus a solar design builder. We explore both traditional design and build approach, as well as using a turnkey solar design builder, which also known as EPC. From experience, we have found that the EPC type of procurement fit the solar PV projects very much. It often quicker and integrates the expertise of the installer early, but however, it does require careful detail in the procurement documents. Bundle the projects and scale. Economies of scale matters. Bundling multiple projects in a single procurement can reduce the cost and simplify the contracting, as well as you can attract more competitive bids. It also helps to standardize the components and design, which benefits the operations and maintenance down the road. Dollar per watt versus absolute contract cost. While the contract cost is a useful benchmark, it does not always tell the full story. We have learned to also consider the cost per watt and the long-term value provided by the system. Especially the solar PV has a big part in the cost savings calculations. System size increase, decrease. Flexibility in the system sizing is essential. Sometimes conditions change from the feasibility study to the procurement or even after the contract is awarded. That forces the project to scale up or down. Having focused on the cost per watt and adaptable design makes the implementation more resilient. These insights have helped us refine our approach and improve the outcome of our projects. Next slide. So some of our projects involve curved roofs. I have attached a few pictures here, which present unique challenges. These roofs limit the use of the standard racking system and require custom mounting solutions. Although it is called a custom, it's actually using some standard racking system with a twist in the design. The racking is mounted on standard roof clips for the support, and we have conducted a detailed structural assessment and used flexible mounting hardware to accommodate the curvature while maintaining an optimal panel tilt. This is an example to show that the importance of flexibility in both the design and installation. Next slide. Another special case involved is installing a ballast system on a slope roof. While ballast systems are common for flat roof, using them on a slope roof raises concern about stability and load distribution. This site originally is installed with an asphalt shingles, and the re-roofing project utilizes 2-ply modified bitumen roofing, which is not common in a slope roof. Typical thinking for solar PV installation will use a standard penetrator hardware to mount the solar racking as a flush mount system. However, there's no standard penetrator hardware. There's no standard penetrator hardware designed for a slope membrane roof system. We address this issue by installing a head-style racking system and strategically place the ballast on the wood truss across the roof to minimize the load on the roof structure. Coordination with the structural engineers is very crucial here to ensure the code compliance and long-term performance. Next.
There's probably a little bit of a delay in the
Sorry. Yes.
Yeah.
So this brings to the end of my presentation. I would like to continue discussion if we're gonna answer the questions now or until the end. I hope this presentation provides some valuable insight. Let me know if you have any questions, and we can take it as part of the program. So now at the end. Thank you.
Thanks so much, Rick. That was very, very interesting. And there's quite a few questions in the Q&A, some for Cajun, some for yourself. If you're able to answer them in the Q&A box, that would be great. And then we'll get to the panel discussion to answer any additional questions from Amandeep or from the audience shortly. We're just going to run through some of the funding opportunities and incentives, and then we'll follow up with the panel discussion and audience questions. So there's many incentives for solar PV out there across Canada. Most of the provinces and territories are offering some sort of incentive for solar PV. This is just some of them here listed on the screen, but definitely reach out to your local utility companies to see what they're offering in terms of solar PV. For those in Ontario, we have Mohammed Yusuf from the IESO here with us today to walk us through some of the new incentives that are out there for solar PV. So welcome, Mohammed.
Great, thank you so much. Good afternoon, everyone. I'm happy for this opportunity to provide some clarifications and on the incentives that's offered for solar PV within the IESO Save on Energy. My name is Mohammed Yusuf. I'm the supervisor for the business program performance. Next slide, please. I thought we start with some background in terms of, what's the electricity demand in Ontario based on our latest annual planning outlook, really expected to grow quite rapidly in the coming decades. And that's prevalent to a lot of electrification, decarbonization efforts that we are seeing, and that really put, increase the electricity and put a lot of stress in terms of additional infrastructure need. So demand side management in particular plays a critical role, as it is one of the lowest cost resources really that can help address system needs. We continue to lead the way in terms of energy efficiency programming in North America. And recently, we have been awarded $10.9 billion for a 12-year funding commitment from the Ontario government for demand side management, really that started in January 2025. One of the key programs that solar PV offering is kind of the home for it is the Retrofit program. And maybe just provide a brief overview on the Retrofit program in the next slide. So the Retrofit program really provides financial incentives to businesses to install capital upgrades that reduce their electricity consumption. These includes non-lighting measures, and there are a number of tracks that can be accessed through that Retrofit program. Essentially, it's focused on commercial, industrial, municipal, colleges, universities, and the likes. For more information, please visit the program website at saveonenergy.ca Retrofit. Next slide. Okay, let's come to under the Retrofit program, and that's how you can access solar photovoltaic incentives, really currently offered under the Retrofit program. The current offering that's really started in January 2025 covers up to 50% of eligible project costs. That includes labor and material for load displacement arrangements only. And it covers two categories: a microgeneration category that is less than 10 kilowatt DC. Eligibility is for $1,000 per kilowatt DC. And a second category is for the small and medium generation that is greater than 10 kilowatt AC up to 1 megawatt AC and eligible for $860 per kilowatt AC. That's capped at 1 megawatt. In terms of incentive, that does not mean the project needs to be 1 megawatt. You can have a larger project, but the incentive will be capped at 1 megawatt. One distinction here is for eligibility for this is for load displacement purposes only and not for a net metering arrangement. Next slide. In terms of resources, if you'd like to know more in terms of documentation and guidelines, you can please visit the Retrofit program website, and there are a number of resources that's available in the links that we have. There's a dedicated section on solar PV, frequently asked questions, really that answers a lot of the eligibility and a lot of the questions to how to access and the process to apply into the program and access these incentives. Next slide. And one great, in terms of if you'd like to direct contact, we do have the Retrofit Support Services support line. This information, feel free to call this number or email them for any information that you'd like on solar PV eligibility or required processes, how to apply, and how to access the incentives. This is really a great direct kind of line of contact that you can access the program and understand a little bit more on how to start your application. All right. Thank you.
Perfect. Thank you so much, Mohammed. That's lots of great information for folks to check out. And we will definitely be sharing a copy of the slide deck so folks can more easily access those links and information. Now it's time for our panel discussion. Hi, Amandeep. Welcome. Thanks for joining. And we'll have Cajun on the panel as well, sort of not taking the place of Sajeev, of course, but jumping in to join in our discussion. And then we'll follow up with audience Q&A from there. So,
yeah, you can sort of guess from the audience questions. There's a lot of interest in this, and I think I hope to sort of cover all these questions as we talked through with the panelists and bring them up. Since Mohammed, you just sort of left the stage, I want to bring back you to the stage and start with the questions on that. Can you, Catherine, can you go back to the slide that Mohammed presented around incentives? I just have one quick follow-up on that for my clarity. So the 50% cost eligible, and then there's $1,000 per kilowatt hour DC. Maybe Mohammed, can you explain that a bit more around with an example? Let's say a project costs $200,000. How is that tied to the capacity, the incentives?
Yeah, thanks, Amandeep. Thank you, Amandeep. I think in terms, so the incentive is capped at 50% of the eligible project cost. So during the application process, I guess applicants will submit the array size, and that really based on it will be based on the capacity of the size of the array. Also, it includes the location, orientation, and the tilt angle, really to calculate the savings per that. So that would be, if it's for a micro generation that is really less than or 10 kilowatt DC, then we will calculate the incentive based on $1,000 per kilowatt DC. Now, you know, as the, I guess, if the project cost is the limiting factor, they could max out up to 50% of that, basically. So they are entitled to that $1,000 kilowatt DC, but on the basically on the cap that there's a 50% of eligible cost. So if
Oh,
let's say,
go ahead, sorry. Go ahead, Mohammed.
yeah, sorry. So let's say, you know, if you look at a 10 kilowatt system, say it costs $30,000 for installation. So at basically of, let's say, including labor and installation, that's 50% of that would be half of that. So let's say $15,000. This is where the cap is, but if your savings based on orientation, the location, and the array size, let's say gets you $40,000 worth of incentive, it will be capped at, let's say, at 15 at that point.
15,000. Okay. And Rick, do you have anything to add to this?
No, I think in general for from our experience, we only have a very few system less than 10 kilowatt. Majority of the system is over 10 kilowatt system in City of Toronto, all the municipal buildings.
And what do you typically find in terms of the incentives get capped out because of the incentive? Or I guess this is a new program. Have you guys looked at this program for any of your projects?
No, we haven't. This is very new. That's part of the study, that the tables that was shown on the slide. It was a very first work that we look into how the incentive will help in different types of buildings that we have, and how it helps in terms of the capital. Based on my study so far, we haven't get with the roof as the roof area that we have on all these buildings, we would never, the incentive will never get into 50% of the project. We won't get to that point. Yeah.
Okay.
Agree, and that's certainly the data we're seeing so far. I think one is the majority of applications are in excess of 10 kilowatts in terms of size. I think the average is around 250 to 300 kilowatts. That's what we are seeing.
Mm.
The cost per watt peak, what we are seeing is really ranges from, you know, if you have a 1 megawatt project, you could go as low as $1.50 or $2 per watt peak. And for smaller projects, you can go up to $4 per watt peak in certain cases. But yeah, and an average around 300 kilowatt systems that we are seeing.
Awesome. So going back to Rick to you, so one of the questions that generally comes with initial feasibility studies around finding out whether it's going to be a good return on investment or not, or does it support some of the fundamentals around decarbonizing these buildings. So the questions that generally comes around is, what kind of upgrades do I need to make the electrical? And would my roof structure or the structure support the installation of these panels? So from your experience, how many of your projects do you have to upgrade the roofs? Or do you have to upgrade the structural to support these projects?
No, we haven't had any projects that require structural reinforcement. We do have some buildings, not a lot, that did not pass the structural requirement. That has multiple reasons. Um, I don't remember the exact settings of the buildings. It depends on quite a bit of different reason. Part of it is the way the building was built, also what existing roofing system or the roofing system going to be replaced will be. Like, for example, a BUR and probably an inverter system will will be much more heavier than a two-ply moppet or a single-ply PVC or EPDM system. So that's part of the reason why when you do a structural assessment, you need to know what you have on the roof or what you're going to get on the roof. So we have not. So in general, we have enough buildings that in our stock. So if there is a buildings that require structural for to get the rooftop like a typical ballast rooftop system, we usually will skip them and move on to the next one. In terms of the electrical upgrade, for now we are in Ontario, we are in net metering or low displacement. So these are all behind the meters. Generally, we do not need to upgrade the whole electrical. There are, for example, in the projects that are similar to the one I showed with the single line diagram, we do need to upgrade the splitter to fulfill the 125% rules as laid out by the electrical code. That's the only upgrade that we need on some of the site. The other site, we just need to add the proper size of disconnect to connect to the building.
Did you end up, so on that same schematic, I noticed there is a transformer as well. Did you guys add the transformer because of the net metering program?
No, that transformer was part of the step down from I believe it was 480 or 600 to a 208.
Okay.
Yeah.
So you were able to feed back
So
using.
the inverter, the system that we have is actually a 208 system. So we can actually connect to that splitter as shown in the screen right now. One of the problems we have I think in Canada in general is the voltage for the inverter, because a lot of the equipment are from this designed for the States and they are 480 and we are 600, at least in Ontario. So we always have to have a transformer somewhere in the design. Yeah.
Yeah, especially when you're talking about the buildings of this size.
Yeah. Like for example, in this one, if in this building, if I have to connect at 600 volt, somehow I can get a 600 volt, or the system is big enough for a three-phase inverter, then I will need a transformer from 480 to 600 to connect it to the main panel. Yeah.
Awesome. Okay. Kajan, any thoughts on based on your work that you're currently doing with the municipalities around the structural and electrical upgrades? How much of those generally are showstoppers in terms of getting this measure implemented in these facilities?
I would say, flat roofs are not a showstopper. It's usually encouraging when we have facilities that have consistent loads and flat roofs that seem to have the structural capacity. You don't really know until you've done the assessments. And a lot of our feasibility studies are at a phase where we have done some high level work, and we recommend going further to do these assessments. That might get ruled out at those portions. Curved roofs are the biggest challenge, especially on some of the ice rinks across Ontario or the country, where they sometimes just use some thin sheet metal. At that point, you likely can't really use that roof at all. Structural reinforcements becomes a requirement, and that drives up the cost and brings down the potential net present value. But yeah, I would say the answer is it really depends on what you're working with, and you really would find out the answer once you go through with the assessments.
And Rick, going back to you around, you've done, correct me if I'm wrong on the numbers, at least 13 of these projects or more?
More net metering. Yeah, more than that. I think close to 20 now.
Close to 20 now. So
yeah.
Generally, typically the initial sort of feasibility costs around the structural and electrical, what are we looking at for the folks? I mean, in your experience, what do you guys have been looking at?
So we do hire structural engineers to look into these sites. Usually we bundle them to about 10 to 15 at least. We can get them down to less than $2,000, depending on what drawings or what information you have available. Like if there's no drawings available, they have to go to a site to assess all of them, then it will be higher. But I think in general, we can get it down to less than $2,000 per site for structural assessment. The structural assessment basically tells you what how much room you have, pounds per square feet on the roof, and then it kind of compare a typical ballast system rooftop solar PV system, and then you can see if you have room for a typical solar system on the roof. That's still that's not a guarantee pass. It just gives you a idea that okay, now you can look into it more detail. As part of the solar installer, the EPC, they will need to design the system in detail, did the ballast plan, and then submit it as part of the building permit. So that will be another structural review in that point, and then the engineer will stamp on the drawing, submit for a building permit.
Okay, thanks.
Yeah.
Now, going back to you on the incentive side, just to kind of put a clarity around, I think there's the only incentive right now is available on the load management. There is no net metering incentives or programs that exist at this point.
From the Save on Energy IESO, the current offering is a load displacement offering. Just to clarify, as part of the current setup, I think there was a question on whether you can switch from load displacement to net metering in the future. I think the current offering is on the assumption that you will continue to be on load displacement and you will not be able to switch to net metering currently. I think from the IESO point of view, we cannot really offer an incentive for net metering at this point, mainly because we cannot offer an incentive for another program by the government of Ontario that's offering benefits through net metering. So at this current point, it is a load displacement arrangement only, but it's something that really we're looking and we're discussing to see if there's any flexibility in the future that we could, consider allowing a net metering arrangement.
Rick?
Yes. So I saw some questions. It's about load displacement, net metering, and how it's connected. So from what I have discussed with our local LDC, the electricity supplier, the Toronto Hydro, so there's no difference between the process to connect as net metering versus load displacement. The only difference from the utility, your local utility, is you don't switch your account to get credits for the excess. So the process to set up a rooftop behind the meter solar PV system is still the same. The output, the outcome, it's the same. The only difference is, let's say you connect, you put your system on the roof, everything is done. Right now in net metering, if you have an excess at that moment, you will get a credit for the account, for the hourly rates, and whatever account that you have. In a low displacement setup, your account setup didn't have that credit. You still export the excess. You still contribute to the community that next to you, I would assume. You didn't waste it. There's no mechanism to stop the generation or the export. Your excess still flows into the grid and go to your neighbors, and everybody's happy. It's the only difference is you don't get a credit. But in turn, if you sign up for the IESO incentive, then you get that part of incentive. Mind you, we haven't got a project going yet. Yeah, sorry.
I guess there was a question around that, is why the paybacks on load management lower than the paybacks on net metering? I think
yes. Can we go to the previous slide? I want to explain that too. I saw that questions. Yes. So again, this is on paper. We haven't done a load displacement project yet. One of the reasons why when you sign up for load displacement, your payback is better because the incentive from the Save on Energy program is very sweet. Sorry, that's the only word I can think of. At 86 cents, 86 cents per watt. That's a good chunk of reduction in the capital cost. If you look at the output, I'll give you an example. For the office building over 50 kilowatt, the first two line. If I use up the whole roof to put a solar PV system on, the system is about 120 kilowatt AC, and your total generation it's at about, I think, 130. Yeah, it's like 1150 kilo. The specific year is usually is about 1100. So your generation is about 130,000 versus in net metering you can get to 145, and you can see the difference between the two. On this building, you didn't waste your I shouldn't use the term waste, but you didn't produce a lot of excess.
Yeah.
Your excess is less than 5% of your system generations.
Mhm.
That's why when you have, in this case, when you have a low displacement setup and get the Save on Energy incentive, which is at 86 cents per watt, that's a significant draw. If your system at 120 kilowatt in Ontario, my assumption is your pricing is around $2 per watt to $2.20 per watt. That's a almost 30%, 40% reduction in your capital cost. And that's why the payback is a lot better when you're low displacement. Again, I do the same thing for different types of buildings at arena, which is also similar. On the last one, which is the community housing that we have, is less than 50 kilowatt. You notice that now because of this building does not have a central AC, so the load is very flat throughout the year, and the incentive based on my calculations, it only benefits a little bit in terms of the payback. The reason is if you look at there's more excess generation between the low displacement in net metering. You're looking at almost a 25% that is excess if it's a low displacement. Mind you, in this case, I would still go with the low this is our study. We're still looking into this, but part of it is the buildings will be going under a retrofit. It will include a AC system upgrade and a heat pump and so on. The load of the building will increase quite a bit. So even in this case, I would suggest to go with low displacement because you still benefit at least a year shorter in terms of the payback. Yeah.
Thanks, Rick, for this detailed explanation. I think this adds more sense to it. So one other question, or a couple of questions that are coming around maintenance of these panels. So you have these projects now for almost 10, 15 years. You get to hear complaints about them systems not working, or maybe they're all working. What's your experience, or what's City of Toronto experience with maintaining these solar PVs, and what are some of the common things you're hearing?
Most of the time, the biggest problem is the inverter. They fail over time. 12 years is our numbers that we find is about 12 years they'll fail, and we actually put in a inverter replacement cost in the business case at the year 12 to replace them. Some fail sooner, some last longer. It depends. The interesting thing is if you go online and look at the inverter manufacturers, they always give you a warranty of 12 years. And there's a reason why they do that, because after 12 years, they fail. Yeah, so inverter is the biggest problem that we have seen. Not sometimes they don't always fail. Sometimes they just have alarm. They need a reset. Um, we don't clean the snow during the winter. I think at one point we at the very beginning of the program before I joined the city, in Fit 1 there's some occasions that we do clean the panel because the Fit program was very good at that time, so they decided to do that. But other than that, we do not have other maintenance. There's a annual maintenance go on there to see any broken panels and so on. But other than that, yeah, inverter was the biggest thing over all these projects. Yeah.
Thanks, Rick. Kajin, coming back to you, and Mohammed, maybe if you have anything to add to this. So the load management program or sizing of these panels require matching that the load that you're gonna get out of these panels to the building load closely or carefully, so you don't oversize the equipment, or you don't, I mean, undersize the equipment, or not get the best benefit out of it. Like, what are some of the tools out there, Cajun, that people can sort of initially use that? And who are the sort of people? Is it sort of goes back to consultants to kind of figure that out with while they're designing it? And then, Mohammed, question for you is going to be on the same line. What helps does IESO provide for the people that are applying to these applications in terms of making sure they're getting the best system or the best value, and then understanding that it kind of complies or matches with their existing building load?
I guess I'll start off. So if the question is about how to get the most out of a low displacement project and how you can kind of evaluate what the correct size of this area would be, I would say, the easiest way to do that is, at least in Ontario, we have electric interval metering. So you'll be able to at least find out, where your peaks, line that up with when typical solar generation would be. The idea is that you don't want to have too much excess. You want to maximize how much you're able to reduce your demand. You might even look at your global adjustment hours, like when are those lining up, if you want to maximize on how you want to shave those peaks. So using interval meters, if you're doing decarbonization projects and you're going to be electrifying systems, you'll have to maybe evaluate these things. Like ideally through these decarb projects, you will create energy models, find out how these new systems are going to be increasing demands at different points of the period, depending on the occupancy, depending on the system types. If you're going to be electrifying heating, obviously it's a different challenge. If you're going to be having more cooling capacity because the climate is warming, this might be something that you might size up something a little higher now, and you can use it, you can take advantage of it later on. These are all considerations that you can take depending on what you have available. But yeah, interval metering is the first place to start. Mohammed.
Mohammed, and then I'll come back to Rick.
Yeah, thanks, Cajun. I think I reiterate this really to, I think really assessing what is the main objective of having the solar PV, and also looking at the real estate that is available, and looking at various design parameters, including what's the solar yield expected in that location, and how can you maximize it, matching your load, understanding the building load profile, and matching the array size as close as possible. Would definitely help get the most out of the installation itself.
Awesome. Rick, anything to add?
Yeah, I just want to circulate back to the figures here. From the studies that I've done so far, I think matching the low for the low displacement to get for the incentive, I think it's really not necessary, unless it's a very special operation. In general, from what I have seen for the building stocks that that City of Toronto has, you would almost want to just maximize the solar system size for the roof size available, especially on buildings that still hasn't been retrofit for heat pump or electrified for uh, or deep retrofit and so on, because chances are your electricity load is gonna go up also. And uh, in general, I think if you do the math, I think if it's less than like 10%, it's pretty much just goes full on the roof and connected as load displacement, obtain the incentives, and then that usually is the best business case. Yeah.
Yeah, and I think what because I understand the challenges of space in City of Toronto, but hopefully I mean, there are a lot of municipalities on this cause that may not have had the same challenge of space. So so for them, I think it's gonna get important, like how much are they gonna invest in, and also considering that once they lower their consumption, and if within that cycle of when to implement it, the best thing to do is first go with your energy efficiency measures, reduce your consumption in the building, demand in your building, and then size your sort of renewable energy sources to tap into that, including if you have any heat recovery available in your system. So I agree. In City of Toronto, there might not be a case to do much of a study because whatever you produce going to be end up using in your building because the space is very limited. There was one question coming in around additional incentives, which I think, and anybody on the call can correct me, applies only to the corporation, which is where the government of Canada offers 30% tax. Again, don't quote me on the accounting terminology here, but it's a tax credit that you get for the investments you make. But my understanding is that that only applies to if you're a corporation, and with the municipalities, I think that doesn't apply. And Rick, I don't know if your understanding on that, because the municipalities to me is not a corporation unless they have a corporation under them that's owned by City of Toronto and that pays the taxes, then it could apply. But otherwise, generally that credit doesn't apply to municipalities.
Yeah, that's correct. I think at this point, we have a few presentations about this tax credit. We haven't figured out how to use it or if we are qualified for it. So we have not account for this yet. And as you said, I believe, yeah, you have to set up a separate company who is to take advantage of this tax credit. Yeah.
Catherine, how do you want to do? I think you said we have 10 minutes. We're gonna keep it for the Q&A. There's a lot of them are being answered by the panelists as they come in, and some of them may have already been covered in the discussion. So how do you want to do this for the last 10? And everybody on the line, please feel free to put in more questions because we intend to either answer them today or just take them back and then answer them with a written sort of response.
Yes, please continue to ask questions, preferably using the Q&A option because Zoom will generate a Q&A report, which will be much easier to circulate after the event as opposed to the chat where it's not logged. I'm just going through to see if there's any major topics or common questions that have been missed. Just bear with me for one moment here. But yeah, it does make sense to get through as many of these as we can.
So let me, Kat, while
here.
you're looking at it, let me take a stab at a couple of them, and I think if we can provide a quick short response and we'll add to it. There was a question about, Rick, back to you. Has the City of Toronto installed a PV system on a pre-engineered roof over ice pads in ice rinks?
Sorry, over a pre-engine?
Yes, roof over the ice pads in ice rinks.
Yes, we do. Almost all the arenas is the first one that got solar PV on. Because usually the roofs are wide open and there's a lot less HVAC equipments on the roof in those buildings. The curved roof that I show in my presentation is an ice ring too. It's a single ply PVC roofing. So we have we have solar PV almost all the arena except for a few that was not caught at the time
Okay.
of the
And then I think there was another follow-up on that is the mounting methods. I'm not sure if you are aware of those, but if not, we can park that for a written follow-up.
Um,
How are the mounting methods for them?
it depends on it depends on the roofing, also the structure. Majority of them are ballast system, almost 90%. The one I show you is the curved roof one. Is the one of the one that we have a penetrator system
Okay.
that was used on. Yeah.
Mohammed, there's a question, maybe you can address this, is proximity to a substation or utility provider important for net metering? Will it affect the financial analysis and overall feasibility of the project?
Yeah, but we haven't really looked at that, at least from our program point of view. But I'm sure in terms of planning, and when you come to the connection process with LDCs, I think that's something that definitely will be part of the connection assessment.
Okay, awesome.
I can add a little bit here.
Go ahead.
If your substation or if the building or your planet solar is connected to a substation that is provided by the utility, you definitely need to account for more times on it. We have experience with that in one of our treatment plant, although the site is actually inside the city facility, but the substation was monitored, not even owned, but it's monitored by our LDC. The connections was a lot more difficult in terms of the review and the engineering of it. Just account for it if you have such incidents in your projects.
Awesome, thank you. There's a question around preventive maintenance or reducing a risk of fire. Do you guys have specifically done anything, Rick, on this, or anybody on the panel knows more about how these additional risk, if there's any, could be eliminated?
No, we do not. All the equipment are CSA ULC certified. All the installations are all ESA inspected. We do not have a incidence of that. We do have inverter fail and they shut down, and it's part of the design of the system. There's no fire occurs from my understanding. Yeah.
Right.
I think we may have time for one more question. Another one for Rick. Have you ever done a solar installation without having done a feasibility study?
Let me think. I don't. There's some projects that I didn't manage as part of other we call client divisions that they handle their project on their own. I kind of help them with the technical side of the process. They they we haven't actually, even those ones I look at it. I did a design. I did look into some of the component of it. At least I have a solar system design uh, for that. I think maybe one or two I didn't have a structural assessment as part of their contract. So, but they do their own structural assessment on the side. I I personally have not. I think if you want to be successful in one of these install, there's different ways to approach it. I know the city, we are lucky we have a little bit more resource. We can look into this a little bit more detail. I know other public sector, such as the school board, they have a different method. They have a third party ownership, like they basically lease out the roof and then let somebody else to take care of everything. So I'm not familiar with that process, but if that's something that other who is interested in that, maybe we can connect with TDSB and see how they manage that. Yeah.
Fantastic.
Catherine, back to you.
Okay, well, thank you so much to our panelists and to our audience for a whole bunch of very great questions. There are some questions we weren't able to get to, but as I mentioned a couple of times, we will generate and release a Q&A document following the webinar just to make sure that everyone's questions get answered. Just to remind everyone of my contact information as well as my colleagues, if you have any further questions, please feel free to reach out. Again, I'd like to take this opportunity to thank our panelists again for all of their time and efforts to share their stories and information with the other municipalities. This is some really important work, and I'm sure everyone really appreciates hearing about your lessons learned along the way and how they can sort of build upon your successes. So thanks so much, Rick, Mohammed, Hamandeep, Cajun.
Thank you.
Appreciate
Thank you
it.
all.
Thank you.
And I'll be in touch shortly with the Q&A document, and there'll be a webinar recording released as well for everyone to take a look at. So thanks again, everyone. Have a great rest of your day, and talk soon.